self-propelled particles, so they are kind of experimental with Janus spheres, and now you have some local slip flow at the particle surface, and that will make these guys to move. And in the second case, let's kind of consider simple rotationally driven spinners. So effectively it would be kind of, for example, magnetic particle with a line with the magnetic field, and then you spin the field. So the particle will spin, and the surface, of course, interacts with the fluid, and we have a bunch of them together to kind of see what happens. And here we have kind of the underlying idea is to see if in this case where we have only translational drive, if you can create rotational structures, and here if you can kind of convert this single particle rotation into some coherent translational motion. Okay, so as Claudio said, I'm in Bordeaux at the moment, and well, part of it looks sometimes like that. Anyway, so here so this is really the work of Zai Shen, who is a really good postdoc working with us on this when we do lattice Boltzmann simulations. He's a super guy on this on the method. So kind of hopefully a soft introduction. So speaking about microswimmers in the beginning, so these self-propelled things, and so it's kind of name suggests they are micrometer-sized objects, and they are swimming, they are moving in a Newtonian fluid. And the nature has realized these in the form of, for example, bacteria. So they are typically rod-like molecules. But you can also realize them artificially in the laboratory, for example, using Janus particles. So now if these two sides have a different response, for example, a field, for example, a chemical field, so then you would have some local slip flow, and that would self-propel from these particles. And an example of a light-actuated Janus colloid moving in a fluid. So these two things are, very different beasts, but it's kind of a common denominator between them is that they swim, so they move through the fluid by some local hydrodynamic stirring. Because they're very small, they move slowly, so they do this in a very small Reynolds number. So effectively Navier-Stokes equation becomes Stokes equation. And here I have an example of a couple of flow fields. So here is the flow field of E. coli, and here is a kind of an artificial liquid crystalline emulsion swimmer. And they look, at least in the far field, they look very, very similar. So this is so-called pusher swimmer. So they are both moving from left to right along the page, and they are kind of pushing the fluid away on the kind of along the director, and then taking it in from the sides. And in the purpose of this talk, I'm really going to consider spherical only for spherical particles. So kind of the practical application would be these artificial guys rather than any bacteria. So just one slide about modeling. So we model these things using reasonably well-known squirmer model, which already been developed or started in the 50s by Lighthill, and then it's been more developed, further developed by other people. And the idea here is that now we assign kind of a slip velocity at the particle surface, given by this kind of equation, and that creates now the flow field far away from the particle and also gives the self-propulsion. So now if you give another particle here, but not, this will be modified, but in simplest case, this is for a single particle, kind of zero volume fraction for single particle in medium. And so now we have a control of the topology. So here's the pusher, as I showed in the previous slide. So this guy moves up the page. And in a Janus particle, well, it would mean that there is kind of more activity in the bottom hemisphere, in the back hemisphere. And it's indeed it's pushing the fluid away along its director, and it's taking it in from the side. And you can also realize a so-called puller, and experimentally it would mean that now you have more stuff going on in the front hemisphere, and this guy is effectively now pulling the fluid towards each other along the axis and pushing it away from the sides. And okay, so but we do really realize finite-sized particles. So with a hard core radius and assign this kind of slip flow in a particle surface, and then solve the Navier-Stokes equation for the fluid flow using lattice Boltzmann. And why would you do this? do these things. So one motivation is kind of a possibility of do active self-assembly. So we know quite a bit about colloidal self-assembly, and now you can kind of use these tools and include the self-propulsion. So these are super nice experimental work showing these things. So here, what these guys managed to do is to kind of self-assemble these rings and these kind of worms, which now these individual particles are simply self-propelled particles, and now due to some electrostatic interactions, they can stabilize these beautiful structures. And here's another example of a kind of two-dimensional self-assembly on a surface. So now you have these kind of Janus particles in a chemical field, and they sediment to the bottom, and you just simply look at them with the microscope, and you can see that now you have a kind of dynamic clustering happening, and the clusters, so you don't get a full phase separation, but the clusters can kind of form and break, rotate, they move around. And in both of these systems, it's kind of thought that now when you see the clustering is stabilized by basically some extra attractive interactions, so here it would be electrostatic, and here now, because it's a chemical driven, so you'll create local chemical gradients, so there would be kind of a phoretic attraction, so that was what the authors postulated in this paper. And now effectively the hydrodynamics, or the self-propulsion, it's just thought to destabilize these clusters. You know, we don't give up easily, so we wanted to see, fine, but is there a hydrodynamic route to self-assembly? And if there is, which I hope, because otherwise I have to stop now, can we tune and design the structures? And we have to play a little trick, but we try to take away from the experiments is that, okay, they sediment, and now you have two different hemispheres. So the ingredient what we bring in here is that now the application of gravity or external magnetic field, if you would like to play that game, would now actually give a torque, which would then rotate the heavier hemisphere towards the more normal. So that would be kind of the minimum energy configuration.
It's platinum covered. The heaviest platinum covered.
Yeah, so this is platinum and gold. And okay, so we don't even try to match any experiment. What we're going to assume is that the front is heavier, so they kind of stop heavy, so the director will point to the wall.
So in that right-hand picture, you said originally a chemical field?
Yeah, so there's a hydrogen peroxide solution.
So I mean, that should be part of the continuum model then, right? Because is it going to get depleted near the...
Yeah, exactly. So you have a phoretic attraction here, which we're going to completely ignore.
Platinum catalyzes the decomposition of H2O2 gives up.
Is there any fine structure of the clusters?
You mean
some sort of symmetry between the fivefold? Or
is here? I don't think so. I'm not sure. I don't think because they move, they break so much, they rotate.
Can you comment a little bit on the dimensions, because it seems like 6.5 is a little bit larger than 10.
Okay, so but there is it's not the scale.
Okay.
Yeah, okay.
Practical was 1 micron you said before. So.
Sorry?
You also
Oh
said
no,
the
but none
minus
of
1
this
micron
is scale
just
here,
a
right?
scale.
No, this is a schematic of the experiment. Oh yes.
You're assuming constant activity, you're not assuming that there is some depletion in the fuel.
Yes, and so my model is literally, so you know, where is my 100? So this is it. So this is all we assume. So and this would be assume that is indeed the flow field what these guys create. But then we only what we're going to evaluate is the hydrodynamic component. So in reality, yes, there would be chemicals. There would be something we want to see. What is the generic behavior basically? Because the hydrodynamics has to be there, otherwise they don't move. Everything else you can tune. That's the physicist justification.
But the motor is the composition of H2O2 over the platinum giving oxygen and pushing away.
Yeah.
Then don't you have gradient of concentration?
Yes, exactly, which gives you the phoretic attraction. Yes, exactly. Which gives you, exactly. So that's what these guys say. Yeah, sorry, I wasn't very clear. So that is indeed what is postulated here. So that, and the propulsion, the hydrodynamics would only break. That's the kind of idea. And I'm just going to be really stubborn and see that, okay, but fine, but can we do something anyway? Because, I don't know, we have computers. And so here is the culprit. So in fact, this is this is motivated by some very nice work from Reynolds group, just building next to us. And what they showed is that now if you have this self-propelled particle pointed directly to the wall, it's unhappy, of course, so it's hydrodynamic torque wanting to turn it away, but now it acts as a pump, right? So, and this is the flow field what it creates. So this is now the pusher. And so you have adjacent particles here, they would be attracted towards the central particle, and that would give you kind of a hydrodynamic route to crystallization in this kind of system. And we effectively want to play a little bit with this. So this is, the hydrodynamics wants to turn the particle away, and now if you just apply something, for example, the gravity like torque, so there is a competition between these two effects, and that's what we want to analyze.
So very naively, the platinum is more heavy. The platinum side.
Okay.
And that's also where the catalysis takes place, isn't it?
Yeah, sure. Okay, so yeah.
Gold does not become.
Okay. So sorry, I'm being sloppy, right? I don't want to model that experiment.
Okay.
I don't. Yeah. Okay. So maybe I should have chosen another movie. But effectively, you'll see the reason why I chose that zoom. But effectively, it's just to.
I was just thinking chemically. So.
Yeah, exactly. No, you're right. So those probably could do exactly the opposite.
Okay.
And there is more complications. So we ignore sedimentation, and that could matter depending on what is the ratio. So we know that now. We didn't know when we started. But, so we ignore a lot of things. But okay, so we're not trying to match any exact experiment. Okay, so here is the idea of the system. So you have a bunch of these particles here near a wall, and then we apply this kind of a torque, which now vanishes, and the director is pointing exactly to the wall. And of course, you know, we can tune the value if you want. So that's basically it what we try to do. And we start from the pushes. So here is the top view of the starting point of the simulation. So now the ball is on the bottom, and that is the flow field. Well, like Claudia said, that okay, the platinum is where the action is, so that would be possibly the flow field of these experiments. And just to look what we get, so despite all the craziness, you do actually get something which looks very similar. It doesn't mean that here it would be hydrodynamics. That's not going to claim. This indeed is probably driven by the vortex, but as a thought experiment, it's somewhat pleasing to see that okay, simply these hydrodynamic fields can create something very similar. And this is indeed what arises from the fact that Reynolds showed. So if these guys are now basically pointing towards the wall, the far field flow field is an attraction, so that would drive the clustering. And now, because there is this competition, so they fluctuate, and there is mixing from the other particles, that leads to the fact that you can have kind of these clusters which rotate or break, reform, those sorts of things. And okay, so if you be fully honest, so the way we can check that we are not actually, even though we get something very similar, we are not agreeing with the experiment if you look single guys, right? So here the single guys are really fast. In my movie, the single guys are really slow, and that is because the single guys are now actually kind of pointing towards the wall, and it's only when there is multi-body interactions when they can kind of synchronize their orientations and start to move. So their conclusions still hold, but it's just a thought experiment that okay, from these simple flow fields, you can get something like that. And okay, so it's a simulation, so you can play with it. So this is pretty but meaningless. So if it does now increase this torque, you can kind of get a different states. So you can get now something. So here you see the fluctuations in the orientations, and then leads to this kind of erratic motion. You can get locked into some So make a stable state where effectively this is kind of schematic, but the orientation would do again rotational motion, and then increasing again, you can have this kind of ferromagnetic or the thing moves. But this is, even I agree that reasonably artificial. However, continue to playing games, so can we do a hydrodynamic tuning, right? So now we have two options, we have pushers and pullers, and I just showed what the pushers do. So now, let's have a look with the pullers. So now it's just effectively just to change the sign on the flow field, so now instead of the flow going away, in the direction, now it's coming towards the particle. And in this case, we get something completely different. So now, as having this kind of communal attraction from the flow fields, we actually have some kind of funny selection of the directionality, and we get these effectively these spinors forming, typically consisting 3 or 2 particles, and that's the only stable configuration with these parameters. And then of course you have the lonely guys here. Now let's see if you can see. Sometimes they can make a bigger cluster, and they would break up. Okay, these guys reverse the spinning direction. Okay, now I can't find any example. But these things turn out to be chiral, so they have some internal chirality, even though the flow fields are completely achiral. And this now, the internal chirality will define the spinning direction here. And that's the color coding. Okay, so here we have a big guy. So you see that it's not happy and okay, it's with the one guy away. So that's good. So the internal chirality gives the spinning direction, and the color coding here is simply just the red spins counterclockwise and blue they spin clockwise.
So the state before the spontaneous is fine. What was the state before they started?
Before they start, okay, so let's see if we can play from the beginning. It's a state line, so they're just pointing at the ball. That's how we initially. So there is some, mixing happening from the flow fields, and that's then drives them. But effectively in a steady state, we find that. So,
and if you have a centrifugal action, so if you spin in a centrifuge, so you have a flow that has a chirality, can you select them?
I don't know. I don't.
I mean, you just spin the fluid.
So if you would put some chirality in the fluid, I really don't know. Yes, well, I try to discuss a little bit of vortex later, but I have no idea what these guys do. Okay, so if you are really brave, we can try to ask a question. Ask a question, kind of if there is some transfer of chirality in the system. And given that we've been brave today, that's what we're going to do. So we can kind of just define a kind of imbalance, so the number difference between the red and the blue, and measure that. So that's shown with this thing here. But okay, so our dynamics is quite slow, so ideally, what you would like to do is run a really long simulation like this, to record this guy fluctuating, from left to right, histogram it in order to get good statistics, but we couldn't do it, we can't do it, we just cannot run it long enough. So what we did instead, we took a smaller sample, about 30 guys, and just initialized them pointing exactly to the wall, so we have absolutely no underlying chirality, and then ran the simulation, measured the kind of what we thought at least as the steady state imbalance, and then repeat it, rinse and repeat 300 times to get statistics. So that is the result of this reasonably painful exercise. And so here is the distribution of the imbalance of left turning and right turning guys. And surprisingly, we observe something reasonably flat. And if there would be no correlations, it should be Gaussian.
Before the sign was always positive, and now it's positive and negative. So they didn't in the previous.
Well, exactly. So that's the point, right? So, Ola, because the time development of this thing is very slow, right? So ideally what you want to do would be to just run very, very long time and to get it to change from positive to negative and histogram. But the dynamics is so slow that we just cannot do it. Simply, I mean, we would still be waiting. So what we did is to try to do the statistics the other way. So we have a smaller system, you initialize the chiral, so everybody points to the wall, and then you run it, and you get some value, so it's smaller than this, so it's stabilized into something, right? And then you do statistically independent realization, so random configurations, 300 times, or whatever, you do it many times, and then you guarantee statistics from that to get this, right? Because you're right, so ideally you would like to see two bumps or something, right? So the sampling is not great, but so don't even want to say much about it, but it looks like that there is some hydrodynamic mechanism to change the chirality. So you transfer chirality from one to the other. So they know about each other. And that's perhaps but it's clearer here. So here is the imbalance of the dimers as a function of the trimers. And you see that there is a strong correlation. So, one species turn clockwise.
I mean, the alternatives could be that if it starts left, it's always left. And if it starts right, it's always right.
Sure.
So if you do the experiment 10 times, it'll be half and half. But you never see the exchange between the two.
Well,
You
so
never
you
see
do
left
see the
going
exchange,
right,
but it's not.
Or right going left. But if they can start.
Sure. But we initialize without chirality, so.
So then it chooses left or right.
Yeah, exactly. But so that's the thing here. So this is like if you do a coin toss, right? So you toss a coin 100 times, and you measure the difference of heads and tails, and there is no correlation, so you get that. So I'm just saying that we put no chirality in, but then eventually.
But the alternative would be that the barrier between left and right is so high that if you start in one, you stay there forever.
Yeah,
but
but that is
one
probably so that is probably the case. So so we have an argument. So it's true. So changing chirality is different than in chiral induction, right?
Yeah.
So we have an argument why, if you have something preformed and something who hasn't yet chosen chirality, looking at the flow field. So I don't have a slide. Well, I have a slide, but I'm not going to show it. But I can show you. So it depends on the vorticity of the flow field. So we have an argument why. We have an argument why would they kind of influence the chirality of others. Again, interesting. And then just very quickly, if you can now use the chirality to have some kind of control of self-assembly in solution. So that's the idea here. So now we just force them to have some chirality. So here in the top row is a homochiral system. So all these guys are spinning in the same direction. And here we find the stabilization of all kind of stable state on this kind of hexagonal 2D crystal near the wall. And that comes from some repulsion, which arises from the pumping of these guys, as opposed to racemic mixture, where now effectively they're not arrested on the lattice, but they are kind of moving, so the dynamics is diffusional. And this is simply just, so this is a kind of zero Reynolds number business, so it's only arising from the pumping of the fluid.
Is 2D?
Yeah,
Very
well,
shallow.
sure, no, it's not 2D, but it's by a wall.
Very shallow. Oh.
No, so you have effectively we hope that well, of course we have to have two walls, right? But we hope that the other wall is far away enough that it doesn't influence the result. So we were checking it. It's as small as possibly can, but we hope it's because numeric, it costs, right? Okay, so you can try to play a little bit of games with that. Now I hope I have time if a little bit to show this second.
Yeah, you are eating in the discussion time, but we had discussion during the work, so I think it's okay. Yeah.
Okay, cool. So so the second system that I will describe very briefly is just if you can have a self-assembly in a very, very simple system, just rotationally driven spherical particles. And those of you of this way inclined, now the Reynolds number matters, so here the inertial effects are important. So if you just look these things in a plane, so now they would be spinning in this plane, at the zero Reynolds number, two co-rotating spheres, the resulting flow field of a single sphere is just an azimuthal, so they would follow the wake of each other, and so they would have this bound rotation, and no matter which kind of distance you put them, they would just keep following, so the distance between them would stay constant. And if you have two counter-rotating guys side by side, so kind of in a same equator plane, so the vorticity goes up, so vorticity in this picture comes towards you guys. Now these guys will just move in a straight line, but again keeping the distance between them constant. Now, if you introduce a small but finite Reynolds number, you get a secondary flow arises, and now the azimuthal flow stays constant, so you still have the rotation around the center point, but now they are repelled because of these inertial effects. And similarly for the counter-rotating spinors, they move, but they are again repelled. And okay, so here is the visualization of the secondary flow, and now the vorticity axis is up, so this guy is spinning like this. And so this is the flow field at Reynolds 10, and effectively there is an advection towards the particle at the poles, and then a repulsion at the equator, which is now this one what was responsible for the repulsion in the previous line. Right, so there is nothing really somewhat interesting in this picture. This has been known since 38. So what we want to do now is to kind of play a little bit of games, put them in a box with Reynolds around 1, volume fraction around 1, and just see what effectively try to see if we can get something out. And just to point out that on their own, so if there's no coupling, they will just spin, so there's absolutely no translational motion. And now, so there's a bunch of them, so they will interact with the flow fields of each other, and we'll see what happens. So this is a top view. It's a bit of a busy movie, but somewhat surprisingly, we see this. So we saw the stabilization of a vortex of multiple vortices, where now the particles, they are spinning around a unique axis, but then they convert the rotation into this coherent translational motion, and this is almost kind of phase separation. So here we just have a clear fluid, all the vortices are surrounded by a clear fluid. And quickly, just so that we can see something similar in 3D. So we've been very worried about this. It's less clear, less clean, and maybe we are not hitting the exactly right points. But so the condensation idea still works. So try to work out a little bit of phase diagram. So this is now really an inertial effect. So we only see it with the Reynolds number of around 1, with the volume fractions around below 10. And okay, so truth to be told, we don't have a huge amount of idea why. So in a low Reynolds number regime, it's clear this one we understand, because you have no attraction, you only have this azimuthal flow. So there you wouldn't expect to see any condensation, because ideally you need some attractive forces to have a condensation. But however, in this end we don't really know. So one way we try to look at it, we try to look at kind of a hydrodynamics just of particle pair. So in a plane of, so we think kind of radial distance and a height between two pairs. So this plane now will be rotating because the whole shebang is rotating. And in a case where we see the stabilization, we actually find that these guys can now have a kind of limit cycle. So they find a solution where they keep it, so the height and the distance is fluctuating, but when they're going around each other, you have this kind of periodic solution. And as opposed to the higher Reynolds number cases, it looks like that it's really this kind of single particle flow field picture is dominating. So now effectively if they're top, so they take this kind of trajectory. And the idea is that maybe these things will act like as a kind of a building block into the large scale phase separation, but the jury is still out there. We haven't figured out. And now very briefly, before Claudia has a heart attack, you can play a game. So here's an example of active-passive mixture. So the yellow things are spinning, the blue things are just inert particles, so they are only affected by the fluid flow. And again here, so this doesn't destabilize the formation of the vortex. So now you see this kind of phase separation of the coherent vertical motion of the spinors, and then the passive particles are really depleted away from the vortex. And just to keeping in line with the session, you can kind of play with chirality, so you can have a racemic mixture, so 50% of guys turning clockwise and 50% of guys turning counterclockwise. And okay, so this is probably not a surprise anymore, but well, you can also stabilize the counter-rotating vortices. And I think that's probably a good point to stop.
Very, very nice. So, questions?
Yeah, thank you for the nice talk. As a soft matter physicist, I appreciate pretty movies. So I have a number of questions.
Is that a compliment? It's really fun.
Among us. Among soft matter physicists.
But I was pretty bored.
I guess on this part with the vortices, the arrows represent, the length of the arrow represents the magnitude of the velocity.
Sure. So that's the indeed, that is the translational velocity.
So they move like a solid disk, so V equal R omega?
Yes,
Yeah.
yeah, surprisingly enough, yes. So it is a
Okay,
solid body
that's
rotation.
surprising.
Yeah.
That's surprising. And then I had
And constant density as well.
okay, interesting. I have a question, another question on the first part, the low Reynolds number. So there, the Stokes equations says the solution of the velocity field should be long range, but you're right next to a surface.
Mm-hmm.
I assume no slip boundary conditions.
Yeah, exactly.
So these velocity fields will go down to, hydrodynamic interaction will be suppressed.
Yeah, yeah.
Do you have a sense, have you calculated how far away do they extend?
Well, I think, so maybe this, where is it? So, okay, so here is the distance between two of these guys as a function of time. So it looks like decaying, okay, so we get some stupid exponents, so there is probably issues, but the flow field on the bow should go 1/3, right? Or 1/2. The beta term goes 1/.
So the distance
Let's
goes
go ahead.
with time?
Yeah, so this is the separation of these two guys.
So they just repel forever?
Yeah.
Is it?
Well, no, okay, so they will stop at some point for sure. Then.
Okay.
So here it appears to decay very rapidly.
So in your first set of hydrodynamic simulations, you had these clusters that seemed to, it looked as though it might be susceptible to modeling by calculation fragmentation equations, where the unknowns are is the mean number of clusters of different sizes at time t. And I wonder whether you checked between the simulation and the experiment, the distribution of cluster sizes.
No. So no, we didn't even try. So I agree that, so these guys did it, so they did really a proper analysis of this. We were basically just kind of curious, can we get something like that out? So these numbers are kind of not unreasonable for what you would maybe expect in the experimental system, but no, we didn't, so the comparison is by because like what Claudia pointed out, we are not, these guys are bottom heavy, if you like. We are doing top, so, wouldn't like to claim anything basically apart from the curiosity that looks the same.
So they become less heavy as they.
No, I just mean that because, like you said, that the platinum is heavy,
Yeah.
so the torque would actually act opposite direction than in our case, right? So
I cannot, curiosity. In your very nice active-passive mixes, the particles were the same size.
yes,
Did you try to have passive of different size, maybe larger, to see if you can act as a carrier or away?
no, we haven't.
But that would be easy for you to try. No?
Sure, yeah. Sure, you could do that. Does it work? Okay. Yeah, you could do that. we've been kind of busy trying to figure out some kind of argument why this should happen. Because if you look at the flow fields, the single particle flow field, I mean, there's nothing there. So we don't really have any argument. So there are these ideas of odd viscosity or whole viscosity in chiral fluids, recently proposed by Vitelli from Chicago, which, you know, but I'm not sure, because that's for a granular chiral gas. So you write a hydrodynamic equation for a kind of granular system. But this is a solution, right? And there is nothing there to give that. So you have an Navier-Stokes for the fluid, and then you have something spinning, and then you just couple them by a boundary condition. So, but you know, so that's me being very worried of checking box sizes and things that it's trying to kill any problems of finite size.
You could have ellipsoids instead of spheres, maybe, if you were patient enough.
Yes,